Lesson 8.1, the idea of a confidence interval. Oftentimes in statistics, we want to answer questions about population parameters, such as how long does a battery last on the newest iPhone on average, or what proportion of college undergraduates attended all of their classes last week, or maybe how much the weight of a quarter-pound hamburger varies after cooking. Now, these are population parameters because we're talking about all iPhones or all college undergraduates. However, it's very impractical to go out and measure the battery life of every iPhone or to ask all undergraduates about their attendance, etc. So instead, what we do is we choose a sample of individuals and we use that to represent the entire population. This is called inferential statistics, where we're using a sample to make an inference or some kind of educated guess or estimate about an entire population. Now, this is an inferential statistics course, and really everything we've learned up to this point has been building towards inference procedures, using information from a sample to draw conclusions about an entire population, such as a proportion or a mean, which we saw in our sampling distributions from the last chapter. Now, last chapter, we were given information about the entire population, and we use that to create the sampling distribution of the sample. But in this chapter, we're doing the opposite. We don't know what the population mean is or the true proportion is, and instead, all we have is the information from our sample. We want to use that to make estimates or conclusions about that population. One of the most common tasks of a statistician is using a sample statistic such as a p-hat or an x-bar to estimate the value about a population parameter such as p or mu. Imagine taking a sample of 20 students and asking how much money they have in their pocket. We obtain a sample mean of x-bar, because it's only about 20 students, not all students, equals $23.8. We would use that to create an interval of plausible values about the true population mean, mu, of how much money all students have in their pocket on average at that given time. Now, the plausible values are going to be a range where we say we think that if we went out and surveyed all students, the average amount of money they would have in their pockets is somewhere in the range of $13.8 to $33.8. We estimate this parameter in what's called a confidence interval. When we talk about a confidence interval, we're talking about an interval of plausible values for a population parameter based on a sample. When we say a value is plausible, it means that we think that the actual average of all students is in that range of 13.8 to 33.8, and we don't think it would be outside of that. So in other words, we would be surprised if it was less than 13.8 or more than 33.8. Now, when we make these, obviously there's not an exact science to it. We're estimating the population parameter, and we're giving a range of values as to what we think the true parameter is in between. And that range can change depending on how confident, quote unquote, we want to be that the actual true parameter is in between the two values that we give. This is called the confidence level. The most common confidence level is 95%, but it varies. Sometimes you'll see 90% or 99%. We call this or label it with variable C, and it gives the long run success rate of confidence intervals, meaning that when we create a confidence interval and say the true average amount of money that students have in their pocket is between these two numbers, it would be said with a certain degree of confidence. For example, the Gallup polling organization recently asked a random sample of US adults about the most important financial problem facing their family today. There were a number of different options, but healthcare costs led the way with 14% of responses. Now, we would use this sample result. This is a p-hat because it's about a sample. We didn't talk to all families or all adults in the United States. We only talked to a certain subset of them, usually in a Gallup poll between 1,000 and 2,000 people. 14% of our sample said healthcare was their main financial problem. We would use that value to create a confidence interval with 95% confidence. And that would give us the interval 10% to 18%. Now, how we actually calculate that, we're going to cover in a later section. Right now, it's all about just understanding what this interval is really telling us. So this value up here is about the sample. Our interval is about the true population P. Notice that I don't have a hat on this value down here, where this one up here does have the hat on it. Okay, so this is about a subset of 1,000 or 2,000 individuals in that range. This is about all adults in the United States. So when we interpret that confidence interval of 10% to 18%, we are 95% confident that the interval from 10 to 18% captures the true proportion of all US adults who would say that healthcare costs are the biggest financial problem facing their family today. So in other words, if we did take the trouble to go out and talk to every single family and find the proportion that would rate healthcare costs as their primary concern, we believe that the proportion who would say healthcare is their primary concern is somewhere in the range of 10 to 18%. Now that was the wordy explanation. We can simplify it with this form of an answer. When we're asked to interpret a confidence interval with whatever level of confidence we're given, this will typically be 95%, but like I said, it can change. We use this form. Okay, and this form is something you're going to have to memorize because you're going to need to write answers in this form over and over again. So we would say we are 95% confident that the interval from 10% to 18% captures the true proportion of all US adults who would rate healthcare costs as their primary concern. The wording on that answer form is specific, and there are a lot of tiny mistakes that you can make that would make your answer incorrect. So to start, it's always about the population parameter and not the statistic. If we were to say we're 95% confident that the interval from 10 to 18% captures the true proportion of all US adults who said healthcare costs were the biggest financial problem, that would be incorrect. This needs to say the word say and not the word said. Okay? And the reason it can't say said is because if they said healthcare costs was the primary concern, we're talking about the people who were included in the sample. They answered the question, they said that healthcare was their primary concern. We got that as our p-hat. That's our sample proportion. We want this to be about the whole parameter of all US adults, all right? So we're going to use wording indicating that this is about all US adults. We want to have that wording right ahead of all US adults. It's good to have true proportion in front of true there. Okay, and we want to note that they would say healthcare if they were asked. The parameter is about everybody in the population, and it needs to be clear when we write our interpretation of a confidence interval. A large company is concerned that many of its employees are in poor physical condition. To estimate how many steps employees take per day on average, the company provides a fitness tracker to 50 randomly selected employees. So here is our sample, 50 randomly selected employees. After collecting the data, they create a confidence interval of 4,547 steps to 8,473. We're being asked to interpret this interval, and we're going to do it using that form that we saw on the previous slide. We are 95% confident that the interval from 4,547 to 8,473 steps captures, and then we're writing that parameter in context. The mean number of steps per day for all employees at this company. Sometimes our confidence interval is going to be given to us in a sentence like it just said, or sometimes it'll be written inside parentheses where it kind of looks like a coordinate point. So this notation right here says the same thing that it said on that previous slide. Now, where does the actual interval come from? Well, there's really two components here. So the first is the point estimate, and that's just the result of the sample. It's the 14% in our sample that said healthcare was their primary cost, or it's the average number of steps of the 50 people in our sample at that company. Along with that, we need what's called the margin of error. That has to do with sampling variability. The fact that when we take a sample of 50 people, 50 employees from this company, we're going to get a different average every time. If we ask 1,000 or 2,000 people to rate their highest financial concern, we're going to get a different proportion saying healthcare costs every time. That said, the population parameter of all adults or all people in this company stays the same. So keep in mind the point estimate is just the result of our sample, and the margin of error is telling us how far at most we can vary from that sample result without being surprised by it. As a visual representation of that, let's tie it back to what we did in Chapter 7 with our population of pennies and choosing a sample from them to find out what proportion were made in the 2000s. If we took a sample of 20 pennies, we would get a p-hat based on that sample. If we did it again, or if we looked at what other students in the class got, we get a bunch of different p-hats, and that's because samples vary. It's natural sampling variation. We have some true proportion of pennies that were minted in the 2000s, but every time we take a sample, we don't match that exactly. It just starts to pile up around that true proportion. Now, the issue is when we take our sample, we only get one p-hat, so we don't see that big spike there. So what we do when we get our p-hat is we move out a margin of error. Right, so basically we move out in each direction, and based on our confidence interval, we say that 95% of the time, what we get this interval from here to here is going to capture that true population proportion within those bounds, 95% of the time. So when we create a confidence interval, we start with our point estimate, and we can visualize it like this. Our point estimate is represented by that blue line there. The margin of error is those purple lines. We add the margin of error to end up out here, and we subtract it from the point estimate, which is exactly in the middle of our interval. So our interval goes from here to here, and we would be C%, 95% confident, for example, that the population parameter lies in that range. If we tie this back to that first example where we were investigating what proportion of all adults felt that healthcare costs was their primary concern, we had gotten the interval 10 to 18%, and we could reformat that as 14% plus minus 4%. This is our point estimate. It was the result of our sample, or our p-hat. And we have our margin of error, which I'm going to abbreviate MOE. If we add 4% to 14%, we get 18%. And if we subtract it, we get 10%. This is how confidence intervals are typically reported in the media. Anytime you see a political poll that says the president's support is 48% plus minus 3 points, that's a confidence interval. So let's also tie in that second example about the true average number of steps taken by all employees at this company. We were given the confidence interval 45-47 to 84-73. We want to work backwards to find the point estimate and the margin of error. The point estimate is always exactly in the middle of those two numbers. So if we just add those two numbers together and cut it in half, we get the point estimate, which in this case would be the X bar, or the average from our sample. So the 50 employees that wore these fitness trackers had an average of 6,510 steps. From that, we move out both directions to find the margin of error. So if we take the top of this interval and subtract the point estimate, we get 1963. That's our margin of error. If we wanted to check it, we could take that number and subtract 1963, and we'll see that we would get the lower boundary of that interval. And lastly, we can use an interval to make judgments or decisions about a parameter. Let's say we were dealing with that interval about the true average number of steps. Health guidelines say that people should aim for at least 10,000 steps in a day. Based on the interval, is there convincing evidence that the employees of this company are not meeting the guideline on average? Yes, there is, because this entire interval is below 10,000. So there is convincing evidence that the employees of this company are taking fewer than 10,000 steps per day on average. Now, if the interval included 10,000, which it does not, so let's change 10,000 to 8,000. Let's say that the health guidelines suggested that adults get 8,000 steps, which is in this interval. Now, this changes our answer. So our entire interval is no longer below this number, and instead there's a portion that meets this. And if this number is anywhere in our interval, we can't say that there's convincing evidence about anything really. So remember, our interval is giving us a plausible range of values. We think that the true average number of steps is somewhere in this range. And if this number is in there, it's plausible that they are meeting that goal. It doesn't matter that it's just a small portion of this interval. All that matters is it inside the interval or is it outside the interval?